Hello and welcome back to the deep dive. I want to start with something that happened to me just this morning. I was looking at a strip of antibiotics,
Oh, okay.
and the instructions were so specific. Take one tablet every 8 hours. Not 7, not 10. Exactly 8.
It's very strict, isn't it?
Very. And then I opened the fridge for some milk, and there's the date stamped on it. Tells me exactly when it's going to spoil.
Right.
And it just got me thinking, how do they know? I mean, is it just a guess? Do doctors just sort of hope 8 hours is the right time?
Well, they're not guessing, that's for sure. There's some very serious predictive mathematics happening behind all those numbers.
And that is exactly what we're jumping into today. We're going back into Unit 3, Chemical Kinetics. But we're moving past the basic theory.
Yes.
We're looking at a topic that is just, well, absolutely essential for your Class 12 board exams, integrated rate equations.
This is a huge one. Honestly, for any student, this topic is often the bridge between just, understanding the theory and actually solving the numerical problems.
It feels like a total shift in perspective, right?
Yeah.
Because until now, when we talked about rate of reaction, we were talking about speed in the moment.
Exactly. Like, how fast is this happening right now?
Yes.
The rate law we studied earlier is instantaneous. It tells you what's happening this very second. But in the real world, we need to predict the future. We need to answer questions like, how long will this medicine stay effective in your body?
Or when will the reactants in this flask be completely used up? That's the real question.
That's the one. When can I go home? So these integrated rate equations, they are the mathematical tools that give us those timelines.
So our mission for this deep dive is simple. We want to understand how chemists and how you in your exams can predict exactly how much of a chemical is left after 1 hour, 10 hours, or even 10 years.
Let's do it.
Okay, so let's start from the very beginning, ground zero. How do we explain the core difference between a rate law and one of these new integrated rate equations?
Okay, think of it like driving a car. The rate law, that equation with the rate constant K and concentrations, that is your speedometer.
The speedometer. Okay, I'm with you.
If you look down, it might say 60 kilometers. That tells you exactly how fast you're moving at this specific second. No.
Right now, yes.
But if I ask you, where will you be in 3 hours?
Yeah.
The speedometer alone can't tell you that.
Because my speed might change. I could hit traffic.
Exactly. Your speed will change. The integrated rate equation is like your GPS. It takes that speed data and it calculates your position over the whole journey.
I love that. Speedometer versus GPS. One is for right now, the other's for the whole trip.
It connects the rate to the time. That is the key.
Let's try one more analogy just to really lock this in. Baking.
Everyone understands baking, yes.
If I tell you this cake is baking at 200 degrees Celsius, I'm giving you the rate, the intensity of the heat right now.
But that doesn't answer the most important question.
Okay, cheers.
When do I get to eat the cake?
Exactly. When is it done?
And to answer when, you need to sum up all those moments of heating. You have to integrate the rate over the total time. That's literally what the calculus is doing.
Okay, now here's where I always got stuck as a student. I think a lot of people do. Why do we need all this fancy calculus? If I know the rate is, say, 5 moles per minute, why can't I just multiply? Say, okay, in 10 minutes, 50 moles are gone.
Ah, the linear trap. That is the biggest mistake students make in this unit. You see, you can only just multiply if the speed never changes.
But in chemistry, it almost always changes.
It does. Think about what's really happening in that beaker. For a reaction to happen, particles need to collide with each other, right?
Right, collision theory, particles bumping into each other.
Yes, so at the start, the beaker is very crowded, tons of reactant molecules bumping into each other constantly, the rate is very high.
Okay.
But as the reaction goes on, what happens to those reactants?
They get used up, they turn into products.
So the beaker gets emptier of reactants. Anyway, it's like a dance floor at the end of the night. Fewer people, fewer bumps.
Huh, I like that.
And because there are fewer collisions, the reaction rate itself slows down. So you start fast, and then it gets slower and slower and slower. It's a curve, you see, not a straight line.
So if I just multiplied rate by time, I'd get the wrong answer. Because I'm assuming the speed stays high the whole time.
That is correct. The integrated rate equation is the formula that actually accounts for that slowdown. It handles the curve mathematically.
Okay, let's pause for a second. Before we get into the heavy analogies, can we just get the proper definition for someone taking notes for their board exams?
Of course. The insert-safe definition is this. Integrated rate equations relate concentration to time and allow calculation of reactant concentration at any point during the reaction.
Simple enough.
Yeah.
relates concentration to time.
It sounds simple, but remember that trap we just talked about.
The linear trap, thinking it's a straight line.
Exactly. That misunderstanding that concentration just drops in a straight line. Unless it is a special case, a zero-order reaction, it never drops in a straight line. It drops exponentially.
Okay, let's visualize this. Exponentially. That's a math word. Let's make a picture. You mentioned an analogy earlier that was perfect. The bathtub.
The draining bathtub. Yes, this is the best way to understand the difference between the reaction orders.
Okay, walk us through it.
Imagine a bathtub. It's full of water. You pull the plug. What happens?
The water goes down the drain.
Right. But does it drain at the same speed the whole time?
No. Actually, now that you mention it, when the tub is really full, it drains really fast. You can hear that whoosh sound.
Because there's a lot of water pressure pushing down.
And what about at the end?
Yeah.
The last few inches.
It just sort of trickles, doesn't it? It takes forever to drain that last bit.
It does.
That is a first-order reaction. The rate depends on the amount of stuff, in this case, water. Lots of water means a fast rate. A little water means a slow rate. The concentration drives the speed.
That makes so much sense. So the graph would be a steep curve that flattens out.
Precisely. But now, imagine a zero-order reaction.
The weird ones.
They are a bit strange, yes. Imagine that instead of just pulling the plug, you attach a special mechanical pump to the drain, and you set that pump to remove exactly 5 liters per minute.
Okay, a constant rate.
Yes. Now, does that pump care how full the tub is?
No, it's a machine. It's just going to pull 5 liters, then another 5, then another 5.
Exactly. Whether the tub is full to the brim or has just a tiny bit left, the pump works at the exact same speed. That is zero-order kinetics. The rate is independent of concentration.
So that's the one that would be a straight line on a graph.
You've got it. That is the only time you can just multiply by time, because the speed is actually constant.
And this whole concept, it was a massive realization for chemists, wasn't it?
Oh, huge. Back in the 19th century, they could see reactions slowing down, but they couldn't predict the endpoint. They had to use calculus integration to turn those observations into predictive laws. Without this math, we wouldn't have expiration dates, we wouldn't have safe medicine.
Speaking of seeing things, I want to try a mental experiment. Let's do our mental movie.
I like these. Everyone, if you can, just close your eyes for a moment.
Okay, if you're safe to do so, please do. I want you to picture a glass beaker on a white lab bench.
Got it.
Inside this beaker is a solution of dark blue dye, a deep midnight blue. This is your high concentration of reactant.
Time 0.
We add a single drop of bleach. Now watch what happens. In the first few seconds, time 1, the color shifts rapidly. It goes from midnight blue to a medium royal blue. It's fading fast.
The bleach is finding the dye molecules very easily because it's so crowded.
Exactly. Now, time 2, maybe a minute has passed. The solution is now a light blue. But notice, the fading has slowed down. It's not as aggressive anymore.
The game of hide and seek has gotten much harder.
Yes. The bleach molecules are swimming around, but they can't find those last few dye molecules as easily, so the fading slows right down.
And eventually, much, much later, it might become colorless.
That visual, the fast fade at the start and the slow fade at the end, that is the picture of an integrated rate equation for a first-order reaction.
And you can see this in real life. If you've ever spilled bleach on a dark t-shirt,
Oh, the worst feeling.
you see it happen. That spot turns orange or white almost instantly. But the edges of the spot, where the concentration is lower, the reaction takes more time. It's chemistry right there.
Okay, so we've got the bathtub, we've got the blue dye. Let's get really serious now and talk about saving lives. We mentioned medicine at the start.
This is perhaps the most common application. It's called pharmacokinetics.
So when a doctor prescribes an antibiotic, say 500 milligrams, they're basically banking on first-order kinetics.
That's right. You swallow the pill, it enters your bloodstream, your body immediately starts to break it down and eliminate it. And this elimination, it almost always follows that same draining bathtub curve.
So it eliminates fast at first, then slows down.
Yes. And this brings us to the very important concept of half-life.
Half-life.
Yeah.
I feel like everyone has heard this term, maybe from video games or something, but what does it actually mean for our syllabus?
It is the time it takes for the concentration of a reactant to reduce to exactly 1/2 of its initial value.
So if I take 500 milligrams of a drug and the half-life is 6 hours,
Then in 6 hours, you will have 250 milligrams left in your blood,
and in another 6 hours after that,
125 milligrams, then 62.5 milligrams, and so on and so on.
It just keeps cutting in half
Yes.
every single cycle.
Precisely. And this is why you have to take the pill every 8 or 12 hours. The doctor is looking at that curve and saying, okay, by hour 8, the level will be too low to be effective. We need to boost it back up.
That is just incredible. It's dosing by calculus. But there's something about half-life that's, well, it's really strange. It's our counterintuitive fact of the day.
Oh, yes. This is a favorite concept for examiners because it doesn't feel logical at first.
Okay, so here's what you might think. If I have a huge amount of something, it should take longer to get rid of half of it, right?
That's what intuition tells us, yes.
So you would think that if I take 1,000 milligrams of a drug, it would take longer for it to drop to 500 milligrams than if I only took 10 milligrams to drop to 5. More stuff should mean more time.
That logic makes sense for zero-order reactions like our pump. But for first-order reactions, it is completely wrong.
Wait, really? How?
For a first-order reaction, the half-life is constant. It does not matter how much you start with.
So if I start with 1,000 milligram, it takes, say, 6 hours to become 500 milligrams.
Yes.
And if I start with just 10 milligrams...
It takes exactly 6 hours to become 5 milligrams.
That is bizarre. The time is the same.
The time is exactly the same.
But why? How does the reaction know to adjust its speed like that?
Well, look at the math itself. The equation for the half-life of a first-order reaction is T half equals 0.693 divided by K.
Okay, T12 equals 0.693 KO.
Now look very closely at that equation. Do you see the letter R for reactant or brackets for concentration anywhere in it?
No, it's just a number and the rate constant K.
Exactly. The starting concentration isn't even in the formula. The half-life depends only on the rate constant. It is completely independent of the initial amount.
That's actually mind-blowing. It means the system has a kind of internal clock that doesn't care how much stuff there is to begin with.
It is very unique to first-order systems. And it's a huge advantage for doctors, actually. It means the timing is a constant property of the drug itself.
Okay, that is a huge takeaway. If you are listening, you have to write that down. First-order half-life is constant.
Bold it, underline it. It will be on your exam.
Now, speaking of exams, we need to make sure our listeners can actually identify this stuff on a piece of paper. We have to talk about graphs.
Ah, yes, the detective work of kinetics.
Right, because in the lab, you don't get a bottle that's labeled I am first order. You just have data. You measure concentration at different times.
And you have to figure out the order by plotting that data.
So let's break it down. There are 3 main scenarios. What are we looking for?
The goal is always to find a straight line. You just have to play with the data until one of your graphs gives you a straight line.
Okay, scenario 1. You plot concentration, just more dollars, versus time, the raw numbers.
Yeah.
And you get straight lines sloping downwards.
If lot versus time is a straight line, it is zero order, like our mechanical pump. The rate of drop is constant.
Easy enough. Scenario 2. You plot that same graph, concentration versus time, but you get a curve.
Okay, that tells you it is not zero order. So now you do some maths. You take the natural log, the ln, of all your concentration numbers.
And you plot that instead. So ln versus time.
And if that gives you a straight line, congratulations, it is a first-order reaction.
This is the most common one in exams, isn't it?
By far. If you see log or ln giving a straight line, it must be first order. The slope of that line, by the way, will be related to minus k.
And what if that's still a curve? Just for completion.
Then you try one last thing, the reciprocal. You plot 1 divided by the concentration, so $1 versus time. If that is linear, it is second order.
So the whole strategy is plot it 3 ways. Whichever one straightens out, that tells you the order.
That's the method. Just keep plotting till one of them works.
Got it. Okay, one last technical trap. Units.
Oh, the units of K. This is where so many marks are lost for no reason.
The rate constant, K, it changes its last name, its units, depending on the order? No.
It does. For zero order, K is mol 1. But for first order, because the concentration terms cancel out in the math, the unit is just time inverse.
Just for a second. Or per minute.
Yes, 0 or more. That's it.
So if a numerical question just gives you a value like KR1.005 and a 1, and it doesn't even tell you the order?
The unit tells you everything. That per second means it must be first order. You don't even need to be told.
That is a pro tip. Always, always look at the units of K.
It saves so much time.
Okay. Wow. We have covered a lot of ground today. From milk going bad to draining bathtubs to calculating medicine doses. Let's try and bring it all together.
Sure, a summary.
All right. So core idea. Integrated rate equations are your GPS. They turn a speedometer reading the rate law into a proper journey timeline so you can predict future concentrations.
And remember the visual, the draining bathtub? If it slows down as it empties, it's first order like most things in nature. If it drains at a steady speed, it is zero order like a machine.
And in the real world, this math is what keeps you healthy. The half-life of a drug determines your prescription schedule.
And don't forget the weird fact. For first order, that half-life is constant. Doesn't matter if you start with a mountain or a molehill.
Yes, and for your exam tip, you have to be a graph detective. If plotting ln as time gives you a straight line, it's first order. And watch those units on K.
Perfect.
Now, before we sign off, we always like to leave you with a little something extra, a provocative thought.
Right. We were just talking about that first order curve, how it gets slower and slower and slower. It keeps cutting in half, half, then half again.
So mathematically speaking, does it ever actually reach zero?
In pure mathematics, no. It just gets infinitely small. It approaches zero, but it never quite touches it. It's what we call an asymptote.
So if you think about radioactive waste, which decays by first-order kinetics, it means it never truly fully goes away?
Exactly. Even after hundreds of half-lives, there's still some tiny, tiny fraction left. So the interesting question becomes a practical one. At what point do we decide that infinitely small is good enough to be called zero? The math says forever, but the real world have to draw a line somewhere.
That is a heavy thought to end on. The math says forever, but real life says good enough.
Indeed.
Well, that's it for this deep dive into integrated rate equations. Don't let the calculus scare you. It's just a tool to predict the future. Keep practicing those graphs.
And we will see you in the next deep dive. Happy studying!